So far, we have only used the CPUs. PyTHon gets most of its powers from its GPUs, though. And we can use Python to program them. Numba cannot just compile to CPU binary code. It can also actually generate machine code for GPUs. The easiest way I already mentioned earlier when we did the Numba vectorize. We can use UFUNCs, like our escape time, and we can vectorize that and give a target. And if you replace the target parallel with the target CUDA, it will actually perform the function on the GPU. And we'll do some speed comparisons in the notebook. But you can do more. CUDA for Python is one of the officially recognized dialects for CUDA. Just like CUDA C++ or CUDA Fortran, CUDA for Python is officially recognized by NVIDIA as one of the dialects for programming their GPUs. But before we go into how to use this, let me tell you a little bit about GPUs and how they are different. Who has used a GPU before? Who has programmed for a GPU before? Okay, then for most of you, this is just a repetition, but just bear with us. CPU versus GPU. Well, a CPU is kind of like a motorcycle. You can get things done quickly. You have low latency to get from A to B. But that's only true if you have a small number of people that you need to transport. One person, great. Two person, okay. If you want to get 50 people from Lugano to Milano, you'll have some problems with the motorcycle. A GPU, on the other hand, is more like a bus. It is slower, will take you longer to get there, but in the end, if you fit 60 people in it, your overall throughput might very well be better with a bus. CPUs are actually optimized for latency. So CPUs try to execute a command that you give it as quickly as possible. They do a lot of optimizations for that. Caches are actually part of that optimization. GPUs, on the other hand, are optimized for throughput. GPUs are made for doing graphics. If I'm rendering an image for a game, for example, at 60 frames per second, nobody cares how quickly I can calculate a single pixel. I want to calculate my 2 or 4 million or 8 million pixels. If I update individual pixels, that usually just creates a mess. So GPUs were designed for workload that does a lot of the same on a lot of data. So originally, they were designed for data parallel workloads. These different design decisions, these different goals, actually led to different architectures and different usage of the die. On a CPU, for the longest time, they were actually trying to hide all the parallelism that was on there. CPUs can do out-of-order execution to use the different arithmetic and logic units efficiently, even if your program code doesn't provide for the needed parallelism. A CPU will execute an if statement or part of an if statement, even if it's not even didn't even reach that part yet, doesn't know if the condition is true or not. And if it fails, then if you didn't do what it thought you would do, it just has to run it again. But if it did already perform what you wanted to do, it can skip that step and go ahead and give you basically internally more parallelism. That requires quite a bit of control logic. The caches, having these different levels of caches going almost up to the speed of the processor, also take up quite a bit of die space on the GPU. On the CPU. On the GPU, on the other hand, we have a lot of arithmetic and logic units with very little control and cache. So little room for the control units that actually all these arithmetic and logic units have to do the same thing. So rather than every thread doing one thing, here a whole set of them has to do the same thing. This is the same thing as if we were using SIMD instructions on a CPU. So these vector units within the CPU, where I said they can do 4 double precision numbers at the same time. In many respects, these are vector units that can 32 double precision numbers at the same time. This different approach that I have on the CPU, where I want to be able to execute a single instruction versus the GPU, where I want to execute a lot and get to throughput, also led to a different kind of execution model. GPUs use very lightweight threads, and a lot of those. On a CPU, the CPUs here have 12 cores, 24 hardware threads, and if each of these 24 cores were starting 24 threads, it already gets messy for the CPU. On the GPU, it doesn't bother it at all. It's actually way too few threads. On a GPU, we hide latency rather than avoid it. What do I mean by that? When I have some tasks that need some data, then on the GPU, I start the data request, then put this task aside, and run the next one. Then the next one will start its data request, at least at the beginning. The first one still probably doesn't have the data. So we continue this, basically sending more and more requests to the memory transfer engine until the first one actually got its data. Now it can work on the data. By the time it's done, the second task has its data and can do its work. So once we have filled the pipeline with data load commands, we get to the point where we can actually execute data one after the other. So we're not trying to get rid of this latency. We're just trying to hide it by being able to keep a lot of threads in flight, thousands of them. Being in flight here means that it keeps all the registers and all the internal information in memory and can access it within 1 cycle, 1 to 2 cycles. So thread switching on a GPU is extremely fast. Due to its origin, GPUs work very well on grid data. So if you can map your problem to a grid, it will usually also work well on a GPU. Modern GPUs, like the newest NVIDIA generations, can actually even handle data that has rather random access patterns quite well. But that didn't used to be the case. So on the Pascal cards that are here, it wouldn't work so well. On the Volta cards that also exist in the systems here, it works very well also with irregular data. When we run on a GPU, we usually talk about kernels. Kernels are small routines that are done by every thread. So just like our MPI program is actually executed by every MPI task, and we have to decide depending on the rank, the same is kind of true for the for the kernels. So let's see what a kernel might be. So here we have our Mandelbrot set again. And look at these two loops here, I and j. Each ij pair actually creates a particular point in the complex plane. And then for each of these points, I calculate the escape time and then assign it to mij. Now, these two steps are independent for each of the iterations. So I could also just put these two in a function and call that function. And this would then be the kernel that I call. To organize these threads, I said I can have thousands of them, millions of them. CUDA uses some organizational scheme based on threads, blocks, and grids. We start with a single thread. Each of these threads executes our kernel, and each of them has an ID. The first grouping is a thread block, and in many respects, this is the relevant group. A thread block always runs on the same streaming multiprocessor. That's the cores within a GPU. Not to be confused what NVIDIA calls a CUDA core, which is actually one of these lanes, one of these vector lanes. The streaming multiprocessors are what's most closely comparable to a CPU core. A thread block will be scheduled on one of these streaming multiprocessors and will stay there. So it's pinned to one of the streaming multiprocessors. That means that all the threads that live within this thread block actually can share memory, share a local fast storage called shared memory. They can easily be synchronized. It is possible in the meantime to synchronize across thread block boundaries, but this is the easiest and fastest one. And it's really the group that you want to use for the parts of the algorithm that need to communicate. So that's not just ideally parallel, but actually has some interactions. Now, thread blocks, since they have to be scheduled on a streaming multiprocessor, also have some limit. For example, a thread block can only have 1,000 threads. Although that actually depends on the architecture. And can vary from generation to generation. So I can have thread blocks 1, 2, or 3-dimensional. So I could say I have a thread block of 1,024 threads just in 1 dimension, or I could say I have a thread block of 16 by 16 by 4 in 3 dimension, or 8 by 8 by 8, or whatever I want. Depending on my problem, I can map the thread block so that it fits my problem. If I want to do matrix-matrix multiplication, I'll probably do a 2-dimensional thread block, because then I can easily tile my matrix. The next level up is grids. Since thread blocks are limited in size, if I want to do millions of threads, I have to somehow organize those too, and that's where the grid comes in. So we have a grid of thread blocks. Each thread block looks the same. Each thread block has the same dimension. I could have, well, in the easiest case, I have a 1-dimensional thread block and 1-dimensional grid. I could have, well, 2-dimensional thread block and a 2-dimensional grid. I could also have a 2-dimensional thread block and a 1-dimensional grid. It really depends on my problem. How does my problem map to a grid? Most of the time, in practical applications, what I've seen, people use the same kind of dimensionality for the grid and the thread blocks. So how do I tell CUDA? Then within this grid of threads that I now have, each thread has an ID, thread ID. This ID can be 1, 2, or 3-dimensional. And in CUDA for Python, I can get it through CUDA grid. So here I'm actually getting the 3 dimensions. If I put a 2 in, I just get x, y. If I put 1 in, I just get x. Which is actually slightly easier than in CUDA C++, where you have to calculate these global IDs. So what does a kernel look like in Python? So I do from Numba import CUDA to get the CUDA features that I need. And then I use CUDA.jit. So rather than using JIT, I now use CUDA.jit as my JIT compiler. Otherwise, this is a regular function, takes several arguments. I can write regular Python. I can get the shape. Here, I assign I and j to the grid to get my position of my Mandelbrot set. Up here, I'm generating something that's called a device function. Device functions can be called from within a CUDA kernel. They are not a CUDA kernel themselves. They're actually functions that can be called from a CUDA kernel. And you'll see that in more detail in the notebook. OK, so defining a kernel is not difficult. It's just like we have done before with our JIT compiler. So how do I actually call it? I have to somehow tell it about all these thread blocks and grids, and how do I do that? First of all, I have to figure out what block and grid size I want to use. So here I'm using an example with a 1024 by 1024 Mandelbrot set. And I just decided to use 32 by 32 thread block. This is a rather explicit way of calculating the grid that I need. So I'm taking my total shape and divide it by the block size here in x. And I say if it's not evenly visible, I take one extra one. Do you know the syntax with the something equal if and else? So in C, C++, it would be the ternary operator. In Python, it's actually written like this. So this defines then a grid that is will hold at least as many items as I need in my M here, or to execute all of M. For this one, it's trivial, because I just know it's also a 32 by 32 grid. But what if I wanted to use 1,000 by, or do 1,000 by 1,000 with a 32 by a 32 grid? Then these extra blocks come in. The launch configuration is then passed in square brackets before the function call. So the function call actually looks slightly different. I have my Mandelbrot GPU, that was just my function name. And then I pass the grid and the block. And then I pass the remaining function arguments. But that's it. Now you have a CUDA program. For those of you used to writing CUDA C++, you might wonder where the memory transfer is coming from. I wasn't doing any explicit managed memory allocation, so it's not the runtime. nor was I transferring data. It's actually handled by Numba. And right now, it's handled in a way that they explicitly transfer data back and forth. So if you do this, it will transfer every array that you passed to the GPU also back. This can actually get expensive. And especially if you have something like this, where you don't really need to move the data in. I don't care what was in M before the kernel. I only care what's in there afterwards. I might want to do explicit memory management. So I can transfer data explicitly with the command CUDA to device. It's one of the typical patterns. You would allocate memory on the GPU and then would transfer some CPU data to the GPU. This command does it all in one go. So it allocates data on the GPU and transfers it at the same time and then gives a pointer to that data back. And we can copy the data that's contained here after we worked on it back to the host. I can also actually do a CUDA device array. This is really just a CUDA malloc. So I'm just allocating some space on some memory on the GPU. I can then run my kernel and get my data back. No easy way actually to transfer data into this variable. I mentioned that the threads that are in the same block can also access shared memory. Shared memory is a user-managed cache. Actually, it is physically the same memory as the cache. And you can tell the GPU to use how much of the memory you want to use as cache and how much you want to manage yourself as shared memory. So the shared cache is also available from within CUDA for Python through CUDA shared array. Here we allocate two shared arrays. We give the shape and the type to be used in a matrix multiplication. You also see some other CUDA commands here. We already had the CUDA grid. You can get the thread index within a thread block through CUDA thread index.x and y. And you can also get the dimension of the grid through CUDA grid. This is what you would usually use in CUDA C++ to then calculate your global ID. This is another typical pattern. I said earlier it's better to ask for forgiveness than for permission. Well, on a GPU kernel, this is not true. It doesn't forgive. It doesn't forget. If you don't check your boundaries, it will write into the memory that you have allocated, or not allocated. So it will write for every thread that it does, it will write in the appropriate memory location, no matter if that was allowed or not. So in CUDA, it is perfectly valid to ask for permission. The return statement here actually means that this thread that runs into this statement will be put aside and is done with. That is one of the best things that can happen to a thread, because it won't block any further execution. If there's a whole thread block, threads are executed in these groups, if all of them run into this return statement, which is often actually the case, or a large part of them, then the execution only takes minimal time. I then need to load data into my shared memory. And down here, there's a synchronize command so that I'm sure that all of the threads have loaded their data item into the shared memory. So that's how you can then use shared memory from within CUDA for Python. CUDA for Python doesn't support everything that CUDA does. For example, texture memory is not supported. But there are not that many items. Dynamic parallelism is actually also not supported. But other than that, most things work. The exceptions are listed in the documentation.